A geometrical definition for an ellipse is that it is a set of points, the sum of whose distances from two fixed points is the same. The fixed points are called foci, and that gives rise to a shape that looks kind of eggy, oblong. Anyway, people call it an oval. For this picture here, we have the foci, which are near the ends of the ellipse. In this case, they're not always like that. An ellipse has a center, and we're going to say that the distance from the center to a focus is called C. And okay, look, for an ellipse, there's a long axis here. You can see it. It goes through the center and the foci, and it connects the two bendiest parts. That's called the major axis. And half of the major axis, that is from the center to the edge, we're going to call A. And then perpendicular to that is what we call the minor axis. It's of course shorter. And half of that, so the distance, the perpendicular distance from the center to the edge, perpendicular to the major axis, we're going to call that length B. The ellipse has two what we call vertices, right? Plural for vertex. Only two, not four. Some people want to put a vertex at the end of the minor axis. That's not a thing. We're going to say this has coordinates A0, the other one has coordinates negative A0, and the minor axis has coordinates 0B, or at least the endpoints of it, and then 0, negative B. I'm not going to put points there though, because I don't want us to think that those are vertices. There are only two vertices. And we'll say the coordinates of the foci are going to be negative C, 0, and then 0, negative C. I'll go ahead and label F2 and F1 for the foci. Now, what this definition says is the set of points, the sum of whose distances from two fixed points are the same. So that means basically pick a point on the ellipse from a focus, don't care which one. Go straight from the focus to that point. Now go straight to the other focus. We will have traveled a certain distance. The thing about the ellipse is it doesn't matter what point you pick on the ellipse, the sum of those two distances will always be the same. So I'm going to call those distances D1 and D2. And the statement is that D1 plus D2 is a constant. Now we can actually figure out what the constant is. We imagine we go from F2 to the edge, so negative A0, and then back all the way over to F1. Let me get a different kind of diagram here. So I'm going to go from F2 to negative A0. There's that little orange segment there. Because remember, it doesn't matter what point I pick to go to on the edge. And then from that ending point there, negative A0, I'm going to go to the other focus. Right? So if I travel the orange and then the green, then folks, it's exactly the same as if I just traveled all the way across the entire ellipse. You see that distance between the focus and the vertex is the same as the distance between the other focus and the vertex. Therefore, the distance is going to be A plus A. So the constant over here is 2A. Now, if we label xy as the point on the ellipse where we traveled, then we can represent the two distances d1 and d2 using the formulas for the distance between 2 points. d1 is going to be x minus negative c, the quantity squared, so x plus c, the quantity squared, plus y minus 0, the quantity squared, so y squared. d2 is going to be x minus, well, now I've mislabeled my focus down here, so I got to fix that. This should have coordinates c comma 0. I had given it coordinates of 0 c or something. Meanwhile, x minus c, the quantity squared, plus y minus 0, the quantity squared, gives us the distance d2. And we're saying that those always add up to 2a. Now I think I need a little more room for the next step I'm going to take. What we're going to do, folks, is we're going to isolate a radical. And then square both sides. I know, this is going to get juicy. So isolating a radical is going to look like, I'm also going to expand inside of the square root. X squared plus 2xc plus c squared plus y squared is equal to 2a minus the square root of x squared minus 2xc plus c squared plus y squared. Now I want to get rid of the radical, and so I'm going to square both sides. Yep, that's right. We're going to have to FOIL on the right-hand side. I'll take us through this quickly, though. You can verify the algebra if you would like. We get x squared plus 2xc plus c squared plus y squared is equal to 4a squared minus 4a times the square root of x squared minus 2xc plus c squared plus y squared plus the square of the square root x squared minus 2xc plus c squared plus y squared. I swear that's what that says there. And we can see that we have some terms that match up, and so we'll subtract out. X squared, c squared, and y squared are all gone. And we can collect some like terms, namely 2xc and 2xc. So we get 4xc is equal to 4a squared minus 4a times the square root of x squared minus 2xc plus c squared plus y squared. This is so fun, isn't it? Check it out. We can divide everything through by 4 and then isolate the remaining radical. Bringing the radical on the left and the xc, subtracting it from the right, we end up with a times the whole square root is equal to a squared minus xc. Well, now guess what? We have this radical that we're going to get rid of by squaring both sides, and so we end up with, by squaring and distributing, a squared x squared minus 2a squared xc plus a squared c squared plus a squared y squared. On the right hand side, a to the fourth minus 2a squared xc, you know what, I'm going to write that as cx, plus x squared c squared. We have one term that matches on both sides, negative 2a squared cx, and it looks like that's all we're going to end up with. At this point, what I'd like to do is gather together everything that has x squared. I'll put it on the side that has y squared, and then on the other side, I'll put everything that doesn't have an x or a y. Factoring out the x squared, then, we're going to have a squared minus c squared plus a squared y squared is equal to a to the fourth minus a squared c squared. We're almost where we want to be, but first I'm going to make some room down here. I move some things up there. Now, folks, we have this a to the fourth minus a squared c squared. I'm actually going to factor out an a squared from that whole thing. And that'll look like a squared times a squared minus c squared. Now, this looks terrible. This is not exactly where we want to be. But if we go back up here, it turns out that a, b, and c are related in a way that resembles the Pythagorean theorem. If we formed a triangle along the semi-minor axis, right, half the minor axis, so from the center to the edge defined by b, and then from the center to a focus, C, then the hypotenuse of that right triangle is going to turn out to be A. As a result, we can say that a squared is equal to b squared plus c squared, which means that this expression that we're seeing, a squared minus c squared, can be replaced by b squared. So we have b squared x squared plus a squared y squared is equal to a squared b squared. Dividing both sides by a squared b squared, it's going to give us x squared over a squared plus y squared over b squared is equal to 1. Now, folks, because a squared is equal to the sum of b squared and c squared, between a, b, and c, a is the biggest of the three. So here we're going to write down that a is bigger than b and a is bigger than c. Now let's see what roles a and b play, not from the picture, but from the equation. If we let y equal 0, then we have x squared over a squared is equal to 1, which means that the x-intercepts will be related to a, right? X will be plus or minus a. If we let x equal 0, then we end up with y squared over b squared is equal to 1, which means that y is equal to plus or minus b. So doing this kind of weird thing of setting a squared equal to b squared plus c squared actually works out so that our x and y intercepts are where we expect them to be with the labels that we've already used.